So today's our speaker is Dr. Chelsea Preble. She's Assistant Research Engineer in the Department of the Civil and Environmental Engineering at UC Berkeley, and also she affiliated in the Lawrence Berkeley National Lab. She earned her PhD from UC Berkeley in 2017. And her research focuses on characterizing the air pollution emission sources, controls, and impact by employing novel science technologies. With that, I will hand over to Chelsea.
Thank you. Let me swap out the slides if you would mind. Thank you. All right, can everybody see these slides? I can hide the floating meeting controls. Okay. Hi. Thank you for that introduction, Akju. I'm really happy to be here to talk about the last set of measurements that we've made at the Caldecott Tunnel to evaluate the heavy-duty emission program development and verification, which is a set of measurements that are ongoing research for us. We've been making measurements of the Caldecott Tunnel. Well, Tom has been making them for decades, starting with his PhD. I won't say the decade because that will age him, but for the current set of work, it started in 2010. So we're talking about more than a decade of measurements at the Caldecott Tunnel. Before I begin, I just really want to quickly acknowledge some really key supporters of this work. Of course, you, the California Air Resources Board, for not only financially funding this work, but in many other ways throughout, including general support and project management, which Chris, George, Akju, and Sungju have all provided. You have allowed us to borrow some really critical analyzers that it wouldn't have been possible to make measurements of nitrous oxide and ammonia without use of the analyzers, so thank you. You also provide really critical information by matching the license plates to the truckers, drayage truck registry, and DMV databases. So thank you for your support with that. And then in our most recent year, we needed a new research platform. So thank you, Jeremy, for helping us to borrow a trailer from y'all so we could make this last set of measurements. Additionally, we'd really like to thank the Bay Area Air District for use of their research van as our research platform for many years. And then really critically, Caltrans and their staff at the Caldecott Tunnel, who have been so welcoming and just really wonderful hosts for this research that they've allowed us to come back year after year. And that's been, without that, we wouldn't be able to make this set of measurements. On the UC Berkeley side, thank you to Rob Harley for just general project and big picture insights on this work, as well as support for the analysis and interpretation of our results. And Rebecca Shugru and James Butler. Becca is now at UCSF for their help with some field and lab work. Diving right in, I don't think that I need to really talk about this in depth, but I just want to make sure that we're all on the same page. Controls and regulations are what are driving down emissions from heavy-duty diesel trucks. In particular, diesel particle filters and selective catalytic reduction systems are standard equipment now on heavy-duty diesel trucks due to the federal emission limits that are set by the EPA. This is a schematic of a commonly used system where the DPF is on the left, the SCR system's on the right. These are both downstream of the engine, so that tailpipe exhaust is coming out of the right-hand side of this figure. Diesel particle filters, or DPFs, are installed for controlled particulate matter. They are installed on 2007 and newer engines at the time of manufacture. It's also possible to install them as retrofits on older engines, although that's kind of a weird California-only situation. These are, they filter the PM before they are emitted at the tailpipe. And then these filters are regenerated through either a passive or active process that involves the intentional oxidation of engine out NO to NO2. And so this can potentially lead to the increase in tailpipe NO2 emissions with use of these systems. SCR systems are installed on 2010 and newer engines at the time of manufacture. They work with a urea water mixture that's known as diesel exhaust fluid, or DEF. The urea decomposes to ammonia, which reduces engine out NOx to N2. It is possible to form nitrous oxide in these systems or have ammonia slip when there's a overdosing scenario with that urea solution. So these are some of the things that we wanted to consider in our current work. Additionally, in California, we have two critical pieces of policymaking, which everyone here should be aware of. So there's the California drayage truck regulation that was implemented between 2010 and 2013, followed by the truck and bus regulation that was implemented between 2012 and 2023. These have accelerated the adoption of these two technologies by now requiring, as of 2023, all trucks to be equipped with a 2010 and newer engine that has both a DPF and an SCR. And the truck and bus regulation is going to be the focus of the talk that I'm giving today. So specifically for this contract, we had a few research objectives that we were seeking. First was to quantify the emission rates from gas and particle phase pollutants of thousands of in-use heavy-duty diesel trucks using what we call a plume capture method at the Caldecott Tunnel. And this was with the goal of trying to assess the emissions benefit of the truck and bus regulation by continuing the record that began in 2010 through the final stages of that regulation in 2023. Specifically, we're looking to characterize the desired effects of using these diesel particle filters and selective catalytic reduction systems for controlling particulate matter, or in this case, we were measuring black carbon and nitrogen oxide emissions, as well as the potential related effects that I mentioned previously of the increased NO2, N2O, and ammonia emission rates. We also wanted to consider the durability of these technologies as they're aging over time. So we've, at the Caldecott Tunnel, made a series of measurements across this truck and bus regulations implementation schedule, where this is a timeline that maps out when we made those measurements and what the corresponding regulations changes were to the fleet. I realize that this is a little overwhelming though. So the simplified version of this is in our prior study where we made measurements in 2014, 15, and 18, characterizing how the fleet was becoming fully DPF equipped. In the present study, we are capturing again that final stage of the regulation when all trucks were adopting 2010 and newer engines. So the focus of this presentation is going to be the most recent measurements from 2021 through 2023, but we'll refer to the prior work when it's relevant. So I keep talking about this plume capture method, and you might be wondering, what does that mean? So we call this the plume capture method because we are literally capturing the plume of passing trucks as they're passing by on the highway. We make these measurements at the Caldecott Tunnel above Highway 24 in the San Francisco Bay Area, where we position our research platform. In the picture here, it's that van on an overpass above the highway. And we extend a flexible aluminum duct down towards the roadway level, which you can see in this left-hand picture here. So we extend that down and position it just above the tailpipes of the trucks that are passing by. So you can see that a truck is approaching the tunnel and our research platform here in this right-hand picture. And so what that looks like in terms of the data, as we're continuously pulling air through this duct, we have this mixture of ambient air and exhaust from the tailpipe of these trucks. And we see a peak in that time series, which you can see in the time series here on the right-hand side of this slide. We use CO2 as our proxy for fuel consumption and the verification of a successful plume capture. And then we are able to integrate the area underneath these peaks and calculate fuel-based emission factors with units of grams of pollutant emitted per kilogram of fuel burned using a carbon balance method. And a key feature of this work is that even if there's not a peak in, say, the black carbon emissions trace or concentration trace like you see in that second truck with the open circles noted, if we do see a CO2 peak, we know that we captured a plume and we still integrate the area under both of those to get a near zero emission factor. A really critical piece of this method is that we need to have fast responding and high accuracy pollutant analyzers in order to make these measurements. So we install a suite of these high accuracy, research grade analyzers in our research platform so that we're able to capture those rapid rises and falls in pollutant concentrations. So in this work for CO2, we used a Lycor LI7000 as our instrument for capturing those CO2 concentrations. For black carbon, we had two different models of an ethylometer from McGee Scientific. One is the AE16, which is an older model that is no longer available, but it has been the analyzer that we've used in our long record of measurements at this location. And we co-located that with the newer model, the AE33, and we found really strong correlation between emission factors that were calculated with both of those instruments. For ammonia, again, we borrowed a Picaro analyzer from you, so thank you. As well as for N2O, which is at the bottom of that stack there. That's the LGR analyzer that we borrowed from you. For NOx and NO, with NO2 calculated by difference, we had two chemiluminescence detectors from Ecophysics that were running in the middle of that stack. And then finally, we had a license plate recognition camera operating at the roadside. So this license plate recognition camera, you can see it on the left-hand picture here. That was our primary camera. It faced towards traffic as it was coming on, so that was able to capture the license plates and the passing time of trucks as they were approaching our sampling platform. We also had a secondary back-facing camera that was installed so that we could confirm the tailpipe configuration of trucks, as well as identify whether or not any truck refrigeration units or TRUs were installed on those trucks. With the transcribed license plates from that LPR camera, we then sent those lists to you, and thank you for matching them again in the truckers, DTR, and DMV databases, from which we could then get specific engine details about each passing truck, including their engine model year, whether there's verified emission controls technologies that were installed, and at times even the engine manufacturer. So this allows us then to match the emissions profile for each truck with these truck attributes, and then on a truck by truck basis have these 4 general categories of emission control technologies. So those are the older engines without a diesel particle filter, which you'll see often in gray. The older engines that had been retrofit with the diesel particle filter, those are going to be shown in blue. 2007 to 2009 model year engines that have DPF at the time of manufacture are in red. And then finally, the newest engines that have a DPF and an SCR system are shown in purple. So you're going to get used to this color scheme because that's what every plot looks like that you're going to see. So with these measurements, we captured a broad variety of trucks. About 10% of the fleet was drayage, but we had, a variety of trucks, including cement mixers, dump trucks, tractor trailer combos, flatbeds, construction equipment. And from our video analysis, only about 6% of the fleet was TRU equipped. In terms of the exhaust configuration, about 30% of the fleet has a downdraft exhaust system, while 70% of the fleet has an updraft. Because of the better capture efficiency with an updraft system compared to the more dilute signal that we get from the downdraft trucks, our emission factors are slightly biased towards the updraft, where our emission factors are about 80% compared to the 70%, but it's a small difference. So diving into some actual results now, the fun stuff. So with this regulation, we've measured the rapid modernization of this truck fleet with near universal use of diesel particle filters and selective catalytic reduction. So I'm showing that here in this engine model distribution, where the gray bars are showing the 2010 fleet before the regulation was implemented, where only 15% of the fleet was equipped with a diesel particle filter and 2% had an SCR system. In 2023, in the purple bars, you can see that there's pretty much just a shift of the whole distribution towards the right, where almost all trucks are equipped with a diesel particle filter. I think only one didn't have a filter in the 2023 measurements, and 98% of trucks have an SCR system. The median age of these engines is the same in both of the distributions at 8 years. But what I think is the really cool thing about this regulation is that long tail of the distribution has been chopped off. And intentionally, this distribution for gray, the gray fleet has been cut short at 1984 just for the visual, when in fact it extends out to 1960. So we really got rid of that long tail distribution for engines that are operating on the road, which I think is so cool. So with this near universal adoption of SCR, we've seen some very dramatic reductions in fleet average NOx emission rates. So you can see this here, where these are the fleet average NOx emission rates in each calendar year of measurements. The 2010 fleet is shown on the left-hand bar, that's in gray. And then you move from left to right, forward in time, where the 2023 fleet is shown on the right-hand side. And so as we go from 2% SCR adoption to 98% SCR use, the fleet average emission rate dropped by 75%. But because we have so much more information beyond just here's what the fleet average was, and we can actually look at subcategories within that fleet, we can also look at how NOx emission rates vary by engine model year and installed technology. So here I'm showing the category average for the 2007 to 2009 model year engines in red on the left. And then I've broken up the 2010 and newer engines by 3 different engine bins. The first are the 2010 to 2012 engines that were first transitioning to SCR. Then in the middle, in that more vibrant purple, is the 2013 and 2015 engine group that was transitioning to OBD requirements, so onboard diagnostic reporting. And then the light lavender on the right side is the set of trucks that are 2016 and newer model engines that are fully compliant with OBD requirements. And so you can see here that on average, the modern engines without SCR emit much higher, 4.2 times higher than the average for all SCR equipped trucks. So that's averaging all the purple bars together. But even amongst the SCR equipped trucks, there are a difference by the, let's call it vintage of the engine model or of the SCR system, where those first generation systems on the 2010 to 2012 engines emit about 5.6 times higher NOx than the newest engines on 2016 and newer engines. Sorry, I'm saying engines so many times, and it's just going to keep happening. And then for just a point of reference here, I've shown the 2010 standard for NOx as that dashed horizontal line. We very much recognize that our snapshot emissions measurements do not capture the full testing cycle that would show compliance with this standard, but we do think that it's a useful threshold to compare our results to, especially since in this uphill highway driving condition, we assume that the engines are hot and those SCR systems are functional. Just a second, I need a little sip of water. So another powerful thing about this data set is that we have a decade's worth of measurements, and we can also consider how these emission rates are changing over time. So what I'm showing here is the category average NOx emission rate for each of these categories of trucks in different calendar years, where the darker shaded boxes on the left-hand side of each of these 3 panels represents calendar year 2014. And the most transparent boxes on the right-hand side of each of these panels shows the 2023 category average. So when you're moving from left to right in each of these panels, you're moving forward in time as those technologies are aging. And we see evidence of increasing NOx emission rates from these aging 2007 and newer engines. In particular, for the 2007 to 2009 model year engines, the 2021 to 2023 average, or the average of these rightmost 3 bars, is 1.3 times higher than the average of the earlier measurements from 2014 to 2018. For the 2010 and newer engines, they were pretty much the same over the last several years. But in 2023, we measured an increase that's 1.7 times higher than previous measurements, which we think could be evidence of maybe deteriorating SCR systems. So we wanted to take a look at that a little bit deeper and try to think about the data in a different way. So here I'm showing a scatter plot of those same averages from the previous slides, but now as a scatter plot versus time. And the way to read this x-axis is that it's years since calendar year 2010. So a value of 4 is equal to the calendar year 2014, and a value of 13 is equal to calendar year 2023. And we put a linear regression through these points, which seems to be a pretty good fit given those high R-squared values. And the slope here, all being positive, is pretty good evidence of these deteriorating performance of these engines with increases over time. So the way to read this would be that, for instance, for the 2010 to 2011 or 2012 engines here in the dark purple, you get an increase of about 1 gram per kilogram per year in the average emission rate for this category of engines. Like I said before, for a subset of trucks, we are also able to note the engine manufacturer of the engines that were installed on those trucks that we measured. And so we wanted to consider how emissions might vary by manufacturer. And you can see here that there are some differences. In general, the PACCAR engines are generally lower than everybody else, while there are elevated emission rates, especially for the 2010 to 2012 and 2013 to 2015 engines from some of these other manufacturers. I will caution though, just note the very small sample size for the International Navistar engines, so take that with a pretty big grain of salt. But in general, especially the Cummins and the PACCAR engines for 2016 and newer engines are performing well with the lowest emission rates on average. I had mentioned earlier also that we were concerned about this potential increase in tailpipe NO2 with use of diesel particle filters. We've previously reported this difference as well as the fact that SCR systems mitigate that undesirable increase. And we're continuing to see that the SCR systems are able to fully mitigate the DPF-related increases in tailpipe NO2 emission rates, where the average NO2 emission rate for those 2010 and newer engines that have SCR are 80% lower than the 2007 to 2009 model year engines that have the elevated DPF-related NO2 emissions. In terms of what that means for the fleet's emissions of NO2, as we have this near full adoption of the fleet using SCR systems, the fleet average NO2 emission rate has decreased by 37% between the pre-regulation and this post-regulation period. So while I've shown that SCR controls NOx well, as again, this reminder for the left-hand figure that you've already seen, we are measuring substantial increases in the emissions of N2O by SCR-equipped trucks. So here on the right-hand side of this figure, or these figures, you can see that trucks without SCR have near zero emission rates of N2O, and trucks with NCR have these elevated emission rates. In terms of fleet average emissions, this means that as more of the fleet adopted more SCR, we saw N2O emission rates for that fleet go up. So again, the SCR percentage is noted on the bottom text of this figure. So we're moving from 2% to 98% with an increase from near zero, what we assume near zero because we didn't measure N2O in 2010, but given that trucks without SCR don't emit N2O and only 2% of the fleet had SCR, we assume that that fleet average was near zero to this elevated value around 0.8 grams per kilogram. We've also seen this trend before, but it continues to show that N2O emissions tend to be highest when NOx emissions are lowest. And this is because N2O can be formed in the SCR system itself, where you have this combination of ammonia and high NO2 conditions from the upstream DPF. And under high temperatures, you can form ammonium nitrate that decomposes into N2O. Similarly, we also see that SCR systems, again, do control NOx, but lead to increases in tailpipe ammonia emissions. So that's the same figure for NOx that I've shown a couple of times now, compared to the ammonia figure, where, believe it or not, there is an actual value for those 2007 to 2009. It's not as much on the screen. Those are the whiskers. So it's a very tight near zero or at zero compared to these elevated emission rates for trucks that have SCR systems. Again, we've published this result before, but we're continuing to see evidence of ammonia slip or overdosing where ammonia emission rates tend to be high when NOx is low. And this is, again, evidence of that overdosing when the ammonia to NOx ratio might be too high in these systems. Changing gears from the nitrogen storyline to now the particle storyline. As the fleet adopted diesel particle filters and then increased in its adoption of the 2010 and newer engines that had both a DPF and SCR system, we saw that the fleet average BC emissions were reduced by 92%. And that comment about the 2010 and newer engines will make sense in just a second, because there is a difference in the BC emission rates by the 2007 to 2009 model year engines versus those 2010 and newer engines. So this is a box plot of emission rates measured for each of these engine model years specifically. And you can see that the 2007 to 2009 model year engines have not only broader distributions, but really skewed distributions where the averages tend to be above or at the 75th percentile, and we have really broad 90th percentile whiskers, compared to the 2010 and newer engines that are shown in purple that have much tighter and less high, or lower, I guess would be the better word, emission rates of black carbon. And again, here I'm showing the standard for PM for 2007 and newer engines as a dashed horizontal line. Same caveat of these are snapshot measurements and not a full test cycle measurement. So it's just a point of comparison. And also really important to note that BC is a major but not sole constituent of diesel PM. So it's not a fully apples to apples comparison, but a majority of those distributions for the 2010 and newer engines are lying underneath that threshold line. I think is great news. Again, considering how these emission rates are changing over time, this is that same figure where if you move from left to right in each of these panels, you're moving forward in time from 2014 to 2023, and the filters are aging. We do see evidence of deterioration in both of these DPF categories. In particular for the 2007 to 2009 model year engines, where the most recent set of measurements from 2021, 22, and 23 are 2.7 times higher on average than the previous measurements in 2014 to 2018. Similarly, it's not as strong of an impact, but we are seeing also elevated averages that are 1.7 times higher than the previous measurements for the DPF and SCR equipped trucks on 2010 and newer engines. Very similar to the NOx story, we also wanted then to consider what this potential deterioration rate might be. We again see a strong linear regression correlation for especially the 2007 to 2009 and the 2010 to 2012 model year engines with a reasonable R-squared value and a positive slope. The good news is for the 2013 and newer engines, there doesn't seem to be signs of deterioration for those newer DPF and SCR systems. But I think that this is something that really merits further investigation, especially if it's maybe a more usable life of these filters, and that this is something that could extend into those newer engines eventually. It'd be interesting to know if at some point these trends flatten out, or if there is a stepwise function where there's complete failure. It's a really open-ended set of questions that I think should be investigated further. And then finally, trying to consider this idea of the high emitter problem in this fleet. It's something that we've talked about before, and you've probably seen a figure like this from us many times. It's one of our favorites, this cumulative distribution of emissions. So here, what we've done is for each pollutant, we rank the trucks from the highest to lowest emitting, and those are ranked on the x-axis from 0 to 1. And then the corresponding cumulative fraction of that pollutant's emissions by the fleet are ranked on the y-axis. And it's just really, really important to note that the top 10% of one pollutant doesn't necessarily overlap with the top 10% of another, because these are individually ranked. But the way to read this chart is that top 10% of the fleet that's highlighted in red, or any fraction, you could do this for any number for that percentage, but the example here is for the top 10%, is responsible for 57% of the N2O that's emitted by the 2023 fleet, 69% of the nitrogen oxide, 83% of the BC, and what I think is pretty incredible, 100% of the ammonia. So these are skewed distributions where the impacts of a few trucks are really dominating a majority of the emissions by the fleet. And again, to just really drive home this idea that the highest emitting trucks of one pollutant are typically not the highest emitting of another species. We saw it previously in the plots that I showed for NOx versus N2O and NOx versus ammonia, but we also see it here for N2O versus ammonia and NOx versus BC. So really to capture this higher emitter problem, you have to think about it from a pollutant by pollutant perspective. And then one last note, or one last thought, is that fixing and replacing these highest emitting trucks is, I think, really the critical next step in terms of further decreasing emissions by this fleet. So as an example here, if we were able to better control the emissions from the top 10% that's highlighted here in this red shaded area. So for instance, if we were able to prevent the ammonia slip from happening on those trucks that were contributing 100% of the ammonia by the fleet, if you controlled that, you'd have a 100% reduction in the emissions from ammonia by this fleet. As another example, if we were able to identify the malfunctioning or for some reason not working black CARB or diesel particle filters and control that BC emissions by that top 10%, we could have the 2023 average go from 0.07 grams per kilogram down to 0.01, which would be an 81% reduction in that 2023 average. And in terms of like the bigger picture of the regulation, this means that if we had these controlled 2023 fleets, that the overall reduction in fleet average emissions of NOx would increase from 75% in the current reality to 91%. And BC emissions reductions would, or yes, if BC emissions reductions by the fleet would increase from 91% to 99%. So we could get further added benefit of these emission controls in this regulation by controlling that highest emitting fraction of the fleet. So I know I talked a lot. I hope you took away some key points, but here's what I hope you took away. With this regulation, we've seen a rapid adoption of these diesel particle filters and selective catalytic reductions, which have led to a near order of magnitude reduction in black carbon and pretty close 75% reduction in NOx between 2010 and 2023. But there's no free lunch, so that comes with concurrent increases in tailpipe and N2O and ammonia by SCR equipped trucks, which now make a majority of the fleet at the Caldecott Tunnel and on the road here in California. We are seeing evidence of increasing NOx and BC emission rates from aging 2007 and newer engines, especially for NOx across the board for all 2007 and newer engines. And for BC, especially from the 2007 to 2009 and the 2010 to 2012 engines. And so we really think it's critical that we better understand what's driving that deterioration and try to prevent it from happening so that we can keep maintaining this emissions reduction that we've gained from this regulation and these technologies, and instead of starting to chip away at that benefit. And then again, the emissions distributions are skewed, so a targeted program to identify and mitigate those highest emitters could further reduce the on-road emissions by this DPF and SCR equipped truck fleet. And with that, I welcome any questions.
Hey, I have two questions. The first question is, what is the time resolution of your sampling, like when you're identifying which trucks are emitting the compounds you're measuring?
So all of our measurements are made at 1 hertz or faster, so really high resolution measurements of each pollutant. And then we only will evaluate the emission factors or integrate the plumes for trucks that we can 100% say that the emissions profile matches this plate. Mm-hmm. So if trucks pass by in multiple succession and it's like really messy, you can't really distinguish one peak from another, we don't evaluate those and don't include it in our data set. So we're really identifying just those individual trucks that we can guarantee that we know that they're matching up 1-to-1.
Okay. And then my next question is related to that, the logarithmic plot. Were you trying to show like the skew of how only some vehicles are contributing to these large averages?
Yeah, so if it was a perfectly distributed set of emissions from the fleet, it would follow a 1-to-1 line.
Okay.
So the fact that we're getting this skewness in those curves, it's showing that high emitter problem and how a minority of trucks are responsible for a majority of the pollution by that fleet. And so that's more evidence for why targeting those highest emitters would lead to the biggest reduction, as opposed to, say, a fleet-wide regulation that would target mostly clean trucks as well as a few higher emitting trucks.
Gotcha. Yeah, and then just with the N2O and the ammonia being so high coming from those trucks, those are other air quality like costs. So is that something that's in the plan for addressing with this new technology?
Yeah, so it's a really great question. So N2O is regulated. There are tailpipe exhaust standards for N2O for 2014 and newer engines that go for the greenhouse gas emissions. Ammonia is not currently regulated, but of course has a pretty big air quality and health impact. So it's another trade-off where you have a climate pollutant, right, that is regulated versus an air quality pollutant that's unregulated. And so I don't know, maybe one of the solutions is we should regulate ammonia, and that would maybe prevent that ammonia slip from happening. Yeah. Any online? Oh, George, yeah. Sorry, I also can't see any questions online because I hid my controls. Okay.
So thanks, Chelsea, for the amazing presentation. Just a comment regarding the ammonia. I'm not surprised that like 5%, it's even less than 10% that's contributing to the, just because like ammonia slip means more DEF consumption and more money. And so I think manufacturers have really tried to dial that dosing of the ammonia like very tightly.
Yeah.
Can you go to slide, I think it was 19, where you're showing all the slopes for the NOx? No, yeah, one? this one. I would
a brand new plot. I made it like 3 days ago, so would love your thoughts.
I mean, we usually plot it against engine age, just to show these increase in NOx. But I would caution about the high R-square values, just because I'm assuming these are the means. But if you plot the entire data, there's going to be a lot of scatter, and the R-square really should represent the entire field, not just like, this is kind of like skewing what the R-square is because we're just looking at the mean, right? But there's a lot of variability around that mean. And then you can do a statistical analysis, see if that increase in mean is really significant or not.
Okay. That's a great suggestion.
And my question was, for the increase that you see in the 2023 fleet for NOx, we do see this uptick, which is a bit concerning.
Yeah.
I'm wondering, do you think there might be an effect of how you're sampling? Is it possible, because you showed at the beginning that there's about 30% of the fleet that's downdraft, and I'm assuming that's something new, and I'm wondering if that's something that's we're seeing more and more that's kind of like skewing.
Yeah, so it's new-ish, but we've always had some downdrafts at this site.
Okay.
And we've always been able to capture some of them. It's not like we've never included downdraft measurements before. I will say, of course, again, an updraft signal is going to be much stronger and much easier to integrate in a way that we think is reliable and accurate. We've done some initial digging into the updraft versus downdraft emission factor results, but we haven't fully flushed it out yet. So maybe that's a great next step of looking deeper into those results.
Maybe look if there are TRUs, more TRUs also.
We did do that, and I don't have the plot for NOx, but sorry, everybody online, close your eyes for a second. Sorry. So this is BC results, not NOx results, but the results for NOx are very similar, where we evaluated those trucks that have a TRU versus those trucks that do not in 2023. And we see a slight difference, of course, here in the left-hand plot in terms of the average, but they're overlapping confidence intervals there. And then if you look at the actual distribution of these emission factors, you see that they cover a similar range and that there's a similar likelihood of a truck with a TRU having a high emission factor compared to a truck without. And so for NOx, it was the same story. So we really think that the TRU, of course, we might be capturing exhaust from TRUs in our emissions measurements here and in this data set, but we don't think that they're biasing it.
Yeah. And the last suggestion would be to look at the fleet age at each calendar year. Maybe there were less new trucks that were sold, and the 2023 fleet is slightly older than the other one. I'm not sure. That could also explain. I'm just trying to see why we're seeing that.
Yeah, no, that's a great idea. I've done a little bit of analysis by the age of these technologies, and honestly, they just looked like the inverse of the engine model year distributions. And so I didn't find a lot of meaning out of that. That's why I didn't present it, but maybe there's a different way to flip that data to make it more meaningful, especially with this new plot like you were talking about.
Thank you.
Yeah.
Any more questions in the user here? Okay.
Great presentation.
Thank
Awesome.
you.
I was interested in the ammonia and especially thinking about elevated ammonia emissions in urban environments and with new PM regulations and the opportunity to have more PM or lower PM standards for ambient conditions. That ammonia could have some impacts from PM formation. And so I just looking at that plot where you have 10% accounts for 100% of the ammonia. Do you feel that is a design where manufacturer or specific manufacturer may be overdosing, or do you feel that is a maintenance issue where it actually is failing, or maybe we don't know?
That's a really good question. And I think the short answer is we don't know. We could all speculate a bunch, right? I will, and again, sorry for everybody's eyes, just close them for a second while I scroll. I know there's a more efficient way to do this. I will say, of course, the trends on this right-hand figure have overlapping 95% confidence intervals. So they very much, it's not like a statistically significant difference here between these engine groups, but I do think that the trend upwards is very interesting. And I wonder, this is my speculation, again, very much speculative. I wonder if one of the ways that these engines are able to achieve such low NOx on the left-hand side is maybe they are relying more on their dosing strategy for ammonia. So the one thing I do maybe want to tease apart more is this contribution of high emitters by these different engine groupings, as opposed to what we've done of considering just the fleet as a whole. So maybe trying to get a little bit more at that question of, is this a persistent problem across all SCR equipped trucks, or is it really just a certain subcategory that's driving this? But in terms of maintenance versus intention versus any of it, that's where we get all speculative. But we should think about it and we should study it, because this, I think, is an important thing to consider.
It would be easy.
Yeah, and I mean, I wonder if it's, again, speculative, but for the OBD requirements, like if you constantly had an SCR system that was throwing an error, perhaps one of the solutions is to throw more ammonia at that so that it doesn't throw an error. I don't know, very speculative.
I guess I got to follow up on so I'm close enough to this, on the updraft, downdraft. So I was thinking about it, back in 2016, we did manual counts of that, and it was about 30% then. And so I was curious, like if you plotted updraft, downdraft versus model year, it might get to some of your questions about bias, if it's staying the same or if it's not, and then how that would affect. Okay. Yeah, that number seems very close to what we measured, I guess, ago. So, yeah.
No, that's a good idea. Okay, so updraft versus downdraft by engine model year.
It helped inform me of that bias, and if there is even bias there, or if it's been the same the entire time.
Yeah.
What that means. Yeah.
Okay. Great
So
idea.
yeah, maybe I can add something like when we did a Caldecott Tunnel, so CARB peaks also deployed the same time when UC Berkeley also deployed. There was we did a check the TRUs in at the Caldecott Tunnel like 2023. Like there are like not many TRU trucks going by, very lower rates, but even though like all of them are not really operating the TRU, so we're using the thermal imaging camera to how many trucks are operating actually during that time. It was less than 50%, and then like only 10%, less than 10% was a TRU, your whole fleet like we were doing. So really lower rates at that time, and also regarding the downdraft and updraft, like newer trucks after 2017, like more than half was about like half was the fleet was downdraft truck nowadays. So the newer trucks will have a more downdraft shape. So we may really wanted to consider the downdraft truck as well. So
Okay.
yeah,
That's great context.
yeah. And then now like we had a lot of questions online.
Great.
So yeah,
Sorry.
I will read the question, the first question first. So this is what from Steve Fritz, Southwest Research. Any thought as to renewable diesel use increasing over the years, and specifically if it explains in part of NOx reduction in 2007 to 2009, known as CR trucks?
We have not considered that, but that is something that we can add to the list of things to dig into.
I don't know how we would identify it. We have data to identify which.
Yeah, so Tom's pointing out that we don't have data from each truck about which fuel they're using, so it'd be tough to tease that apart from the data that we have unless we had some other, I don't know, statewide indicator of, or Alameda County indicator of how much renewable versus standard diesel trucks are running on. So that might be something that's certainly an effect, but I don't know if it's one that we would be able to actually evaluate beyond just saying it might be present.
So Steve has an additional question that,
Great.
yeah, oh, sorry, like it's thought as to if 2010 to 2012 Navistar trucks having higher NOx could be that they had a number of NOx credit engines out there in that time period.
Oh, so you're saying that they're not actually SCR equipped trucks because they had the credit instead of the engine manufacturer had the credit. That's possible. Again, we don't know that from the data that we have available unless it was obvious from the engine manufacturer that if there was an engine manufacturer that had a majority of their trucks were on credit and not with SCR systems. So yeah, in our work, we're assuming if you have a 2010 and newer engine, you have a DPF and an SCR, but we recognize that that's not always going to be the case for this very reason.
So if Steve, like you have additional comments or questions, you can go ahead and unmute your mic.
Okay, can you hear me?
Yeah.
Okay. So excellent presentation, very, very informative. So I think if you have the license plate number of the truck and you can get the engine family, perhaps as part of the registration, you can go back and get the NOx that has an FEL level much higher. When we worked with CARB on it was one of the Zanzev studies, we had like a 2012 Navistar dredge truck that we sort of did that. We went back on the serial number engine family on the engine, and we're able to see that it was a emissions credit consumer at a NOx level. The standard then was 0.2 grams per horsepower hour, and that truck was
Mhm.
1.2. So if you go to your slide where you had a by uh, vehicle or engine manufacturer, you had a whole bunch of the Navistars there in that time period, right?
Mhm.
2012 was notably higher. I suspect what you're seeing is a bunch of still EGR equipped engines, non-SCR equipped,
Yeah,
driving
I
that
will.
car.
No, that's a great suggestion, and I'll definitely look into it. I will just note that there's only 6 international Navistar engines from the 2010 to 12 in this plot, and um, we did do so. So it is possible, but I don't know if they're the ones that are driving the trend that we showed. We did do an initial analysis by engine family, trying to actually get at what you're suggesting, not from the perspective of whether or not there is EGR or SCR, but just in terms of these trucks meeting their FEL. And we had such a small sample size and such a variety of different trucks. It was actually just kind of not clear what was going on. But I can try to revisit that to see if maybe there's some useful information that we could
Right.
tease out of that
Okay.
data.
And back to
But
the
thank you.
earlier question on renewable diesel,
Yeah.
then there is the CARB fuels folks have statewide how much of the fuel pool is year by year renewable or renewable bioblends and dominated by renewable. So you could make some broad estimates there. Because I think today, like, you know, 6 out of 10 gallons of fuel dispensed in California is renewable/renewable car or renewable or bio dominated again by renewable. So that program's been extremely effective. But if you go back 3 or 4 years ago, there was, 5 or 10% of the fuel pool was renewable. So you
Okay.
probably would see a shift in the last few years of
Mm-hmm.
NOx on those pre-SCR engines going down, and what could be driving that. And it could be the fuel.
Okay. So wait, sorry, just to make, so you're saying that for the red bars here, you would expect some of them to go down
Um,
with
yes,
use of,
both the blue bars and the red bars in time. The far right bar, how could it drop so much in the last bar in 2023? Would be one scenario would be the presence of that much more renewable diesel in the pool.
I see what you're saying. My counter thought to that is just that there's actually a pretty low sample size for that bar. It's only 19 trucks. And same
Yeah.
with the blue bar, it's only 27. So since we know that emissions are skewed, I think it might just be not capturing all of the high emitters on the road because there's just so few of these trucks still on the road in that calendar year.
Yeah, could be little both.
Yeah, no, I'm not discrediting that. I think it could possibly be both, but yeah, it might be hard for us to tease that apart with the data that we have, but it's an interesting thought that I hadn't considered yet. So thank you.
And then one final thought on all that is the red bars there, the 2007 to 2009 trucks and the increasing PM over time.
Mm-hmm.
The reliability, the filtration efficiency, the filter is one thing, but you think about EGR equipped engines as they get older and older, the engine out PM is probably getting much and much worse, putting so much more burden on the filter
I
that
see.
even if the filtration efficiency is constant, you're going to see an increase.
Okay, so you're saying it might not just be a filter issue, it's an engine degradation issue as well, or a combination of the two.
Yeah, I'd put most of that emphasis on the engine.
Okay, that's helpful. Thank you.
Mm-hmm.
So the next question is Suji Chung from ARB. Would a type of fuel such as biodiesel or renewable have any impacts to your study?
Again, potentially, but it's not something that we could tease apart with the data that we have because we don't know what each truck that we're measuring what fuel they're using. So I think in this case, we're relying on the power of numbers and that our sample sizes are generally large for these considerations by control technologies, that it's capturing the real trends that the on-road fleet has.
The next question is Whaley. Ammonia emissions, all slip or including some tailpipe emissions? Have you compared your study with the University of Denver studies done at Port of Los Angeles weigh stations in SoCal and Northern California? And then why there were still so many 2007, 2009 vehicles on road in 2021 through 2023?
Sorry, it was hard to hear. Which one are we looking at?
Okay, sorry,
this one. Oh, so yeah. For our prior work, we have certainly compared our work to the University of Denver studies. That's on a good next step for us, is that we need to consider those most recent work out of Denver to see how our emission rates are comparing. So thank you for that.
This other question was ammonia emissions all slip or including some tailpipe emissions? That was first one.
All slip or including some tailpipe emission. I'm not sure I understand the difference between what we're talking about there. And my understanding is that ammonia slip is still at the tailpipe.
Correct. So, yeah. And why there was still so many 2007 through 2009 vehicles on road in 2021 and 2023?
Oh, yeah. So, I mean, it was a phased implementation schedule of turning over that last fraction of the fleet, and the 2007 to 2009 engines didn't have to make that change until the final year, I believe, which we can go back to my very wild timeline plot to verify. Sorry for your eyes, everybody. Yeah. In the very last year, the 2007 to 2009 model year engines were replaced with 2010 and newer.
And the last question is that what were the average vehicle speeds at the measurement site?
That's a great question. So yeah, the average speeds, which I think we have here in kilometers per hour, which I always have to think really hard about what the original conversion that I had in my mind for miles per hour. It's around 25 to 80 miles per hour, depending on the truck. So if, you know, a cement mixer is fully loaded up, it's really putt-putting up that 4% uphill grade versus like a completely empty, like just a cab could be flying up that hill. So really variable speeds, especially compared to the measurements that the Denver team makes at the port sites or at the weigh stations, where those trucks are essentially like creeping through their setup. It's not a fully complete comparison when we consider these measurements compared to that Denver work.
Again, from Whaley, so have you measured any natural gas trucks? If any, how did you handle the different exhaust pipe position? And what were the ammonia emissions compared to diesel trucks?
Great question. So back in 2018, we tried to measure methane from CNG trucks, and I think we saw 3 trucks and no methane. So we didn't continue those measurements. In this data set, specifically, we've isolated class 7 and 8 diesel fueled trucks. So there are no CNG trucks included in this data set. And I think the fraction of CNG is still extremely low at this site. It's still a handful in the license plate returns that we get, as opposed to anything significant.
And, next question is Eric Philly. Any predictions for N2O and ammonia trends with the newest 0.05 gram and future 0.035 gram NOx certified engines in 2024 and beyond?
That's a great question. I will say anything I could say about N2O and ammonia with those trucks would be like beyond speculative. I think we would really need to make some measurements. But what I can show you, and again, I'm so sorry, just close your eyes. It's gonna happen again. We have considered the distribution. Sorry. Here it is. Okay. We have considered how the current emission rates for the newest engines, the 2019 to 2022 engines, compare for that 2010 standard versus the 2027 standard that's coming up. And a majority of the emissions for these engines meet the current standard, but a majority will not meet that the new low NOx standard that's coming up. Nor would they meet the California specific standards that you mentioned. So I think it'll be interesting to see how the manufacturers tackle this problem and get these NOx emission rates down. Perhaps if we're going to follow our logic for the ammonia and low NOx story, is maybe there will be more NOx or more ammonia, which would mean less N2O, since we know that they are inversely related typically. But that would be very much like speculative is not the right word for it. It's more than speculative.
Right. So,
sure, it would be very much a wag.
right. So actually, the previous question regarding the speed at the Caldecott Tunnel, Dan Phillips CARB, our colleagues, he also left a comment, and in CARB's, so because we also measure the speed using the LiDARs. So the speed measurement, we found very few trucks above 55 miles per hour, because it's kind of a hill and entering the tunnel. So with the bulk like 35 to 45 miles per hour during the free flowing conditions when you were sampled, that's kind of what we had record.
That's
Thanks,
awesome.
Dan.
Now I can
then,
say that
yeah,
more
and then
specifically.
had another, this is kind of comments that he said, historically license plates alone are not always enough to get in engine family. It depends on whether, for example, they are in our drayage register. Otherwise, it's hard to get the information.
Exactly.
And yeah, in practice, you can often narrow it down to a few families, but that is not always enough for granular engine info. So that's the comments. Thank you, Dan.
Thank you, Dan. That's great that I'm not imagining things. That's real, what I found.
And then there was another from Adri. So were majority of the screened trucks local or out of area or states?
I would say a majority are certainly within state, but it's not to say that we don't see out of state plates. There's also a fair amount of out of state. I could try to quantify that with another round of data analysis. In terms of local versus not, that's a harder question for us to get at. I don't know all the activity patterns again from every truck. So I think it's probably a nice mix, but we wouldn't be able to say without actually following the trucks.
So, and then I think that's all from the chat box. So if there's more questions, please raise hands and then you can ask questions. Actually, one more from Eric. Oh no, it's just look forward to seeing the presentation. So yeah, please raise hands if you have questions.
And feel free to reach out if anything comes up in your minds later after you've had a chance to let this sink in. Happy to chat about this anytime.
So I don't see any hand raise. So I think we can adjourn this meeting. So thank you, Chelsea. And then thank you everyone to joining our research seminar. Thank you. So you can have the, from the our project webpage, you will see the recording of this seminar, and we will add the presentation and final report sometime soon. So thank you, everyone.
Thank you.